completing the MATLAB grader, I'm extending assignment 7 due date by 2 days to give you a chance to try your programs with it. However, due to the end of the semester coming up, the last assignment, which will be on applying some of these geometric transformations, you need to get started on next Tuesday. It'll be available long before next Tuesday, but in any case, my intention was that you got started on next Tuesday and you still need to. That'll give you 10 days to finish it and still have us get it graded in time for you to study for the exam. Any questions on that? Any questions on anything? Okay, so we were talking about rotations. And just to summarize what the things we're talking about, we're talking about 5 different ways of representing a rotation. The first is by a rotation matrix. We've been talking about that for a long time. But let me remind you, it consists if we're in 3D, it consists of 3 vectors. Each has a column. And the first one is the image of U1 under the rotation. The next one is an image of E2 under rotation. And the third one is the image of U3 under rotation. So if E1 and E2 and E3, our convention are EX, EY, EZ. That is to say the pure X vector 1, 0, 0, the pure Y vector 0, 1, 0, and the pure Z vector 0, 0, 1. And after the rotation, the E1 vector, the EX vector has rotated into U1, the UY vector into U2, and the UZ vector into E3. Okay? And so the application to an arbitrary vector t, simply you multiply by the rotation matrix to get RT. Okay? Clear so far? We're going to be talking about the number of degrees of freedom to describe something, or equivalently, the dimension. And the dimension of an entity is the number of degrees of freedom, the number of free choices you have to get a possible vector. And for an n vector, it's n minus the number of constraints. Each constraint lowers the dimension by 1, lowers the degrees of freedom by 1. Okay, so for this thing, how many degrees of freedom for U1?
3.
Good idea, but no, there's a constraint. 2, because there's one constraint. What's the constraint? No. I'm just choosing U1. There's no other U2 or U3 around. It's sum of the squares equals 1. That's a constraint. Right? It's not any old vector. It's a unit vector. Right? And so it has a constraint. Right? And so there's one constraint, and therefore U1 has 2 degrees of freedom. Even though it's got 3 entries, it's a vector of dimension 2. Yeah.
So is this definition of dimension pretty general? Like, that's not like a spatial 2-dimensional, like 2-dimension. It's just like.
Well, it is a 2-dimensional space, in fact. Because.
Oh, yeah. No, you're right.
Okay. Because it's limited to the unit sphere, and the unit sphere, just the boundary of the sphere, has only 2 dimensions. Right? It's a thing that you can walk at any given point. You can walk in one direction or in the orthogonal direction, but once you've determined that, you've covered every other direction is a linear combination of those two directions. Only 2 degrees of freedom on the unit sphere. Okay, so U1 has 2 dimensions. Now, U2, how many constraints does it have now, given that we've already chosen U1? And somebody's already suggested the answer to that one. How many constraints? Okay, I see one answer, more answers. More people I want to hear an answer from. Want to give me an answer?
2.
2. What are they?
So sum of the squares 1 orthogonal to the first one.
That's right. Right. The 2 constraints. It's orthogonal to U1, that's a constraint. Sum of the squares, it's a unit vector, that's another constraint. So there's only 1 degree of freedom in U2, given what you have U1, right? So far we've got 2 plus 1, 3 degrees of freedom. Okay, U3. How much freedom do you have for that once you've chosen U1 and U2? 0. U3 is just U1 cross U2. Once you know U1 and U2, you know U3. There's no more degrees of freedom there. And therefore, there are 3 degrees of freedom total in this rotation matrix. Right? So it's not surprising that it's going to live on the 3 sphere, which has 3 degrees of freedom. I made a mistake, a foolish mistake last lecture, and put the wrong indices on these spheres. The unit sphere in 2 dimensions is a 1-dimensional thing, right? Because it has a constraint of being unit. And it is the unit circle. And in a unit circle, at any given point, you have only one possible way to go, plus or minus in that direction. Yes? And in the unit circle, the constraint is that x squared plus y squared equals 1, right? The 2-dimensional sphere, which is understood to live in 3 dimensions, we say embedded in 3 dimensions, is a thing that looks like beach ball. It's in 3 dimensions, x, y, z, and the constraint is x squared plus y squared plus z squared equals 1. That's called S2, the 2-dimensional sphere that is embedded in 3D x, y, z. All right? The 3-dimensional sphere embedded in 4D is called S3. It's a 4-tuple w, x, y, z, but with the constraint that w squared plus x squared plus y squared plus z squared equals 1. And that thing doubly covers rotations, because you can have a rotation, positive angle of rotation around an axis, or a negative angle of rotation in the opposite direction axis. The axis can be in either sense. Cool. Okay? So please pardon my error from last time. Correct your notes. S3 has this form, S2 has this form, and S1 has that form. Okay? Okay. The next representation we talked about, but that I don't recommend you're using, but you need to know about, is 3 Euler angles. Rotation about the x-axis, then the rotated y-axis, and then the doubly rotated z-axis by theta x, theta y, and theta z. How many degrees of freedom? How many free numbers do you have here? Three. You can choose theta x, you can choose theta y, you can choose theta z, they all work. No constraints. Okay? Not surprisingly, it's still 3. The main point is that the collection, a set of some entity, the set of all rotations, for example, but it could be the set of all translations or the set of all any set of geometric transformations. That set itself has a fixed number of degrees of freedom, and every representation of it is going to have that same number of degrees of freedom. 3 here, 3 here. The next representation of rotation that we talked about was a rotation vector v giving an axis, the unit vector v, v over its magnitude, and an angle magnitude of v. And that thing was represented by what I call the incremental rotation matrix A sub v, and I'll explain that in a moment. But here it is. It has 3 entries, Vx, Vy, Vz, the 3 components of V. How many free variables? 3. Vx, Vy, and Vz. Right? Or put another way, you have an axis. How many degrees of freedom in your axis? Axis is a direction that lives on the unit ordinary 2-sphere. How many possible directions are there? Well, the number of points on that sphere, latitude and longitude, 2 dimensions, right? 2 dimensions for the axis, 1 for the length, 3. Right? Got it? Okay. The AV matrix is an antisymmetric matrix. It has 0. An antisymmetric matrix has the relationship that A transpose is minus the matrix. For that to be true, obviously, its diagonal elements have to be minus themselves, and therefore they all have to be 0. And the ones off the diagonal have to be negative of the ones on the corresponding ones reflected across the diagonal. So you have Vx, Vy, Vz, and then minus Vx here, minus Vy here, and minus Vz here. All right? And that's incremental in the sense that you have a rotation, and then you want to apply a little bit more of that rotation, okay? And this is the matrix you multiply by to get epsilon amount of that further of that rotation. Okay, so we can characterize a rotation by its incremental application or its full application. Its full application has the identity matrix added to it. It keeps it the same, and then on top of that you incrementally apply AV. The fourth one we talked about, we started to talk about, and there'll be much more about it in this lecture, is the Unitquaternion. I'm calling it WABC, although the slides say WXYZ, but I'm trying to not confuse you with the X being the X direction so far. And it is understood as W times the Unitquaternion in the real component, which is 1, And there are three imaginary components, one in the I direction, one in the J direction, and one in the K direction. K, these are all imaginary number counterparts. As you will see, all of them have a square equal -1. I squared is -1, just like in complex numbers. J squared is -1, and K squared equals -1. Okay, but you'll see how they're different in a minute. The unit quaternion has the coefficients, sum of the squares equal to 1. A constraint. How many free variables? How many variables are there, first of all? W, A, B, C, right? Therefore, how many constraints? 3 free variables. A dimension 3 entity, 4 minus 1, right? Still 3. We will see, well, I told you last time, but I'm repeating now, that the W term is cosine theta over 2, which means that from the W term, if you take the cosine inverse of it and then multiply it by 2, you get the angle of rotation. So it has the angle of rotation here. And A squared plus B squared plus C squared ends up having to be sine squared over 2 because cos squared plus sine squared is 1, right? And this is unit. Okay, and we will see that when you apply that to a vector t, what you're going to do is to take the unit quaternion. I've just reminded you with the hats that they are unit. And you'll see that we will represent 0t, we will represent the vector as the quaternion in which w equals 0 and t, the thing you're applying it to, appears, its 3 entries appear in the A, B, and C slots, the I, J, and K slots. Okay? And Q inverse turns out to be, and we'll see that in a moment, W minus A minus B and minus C. And that makes a lot of sense because the ABC together give you sine theta over 2, and sine of minus theta over 2 is minus sine theta over 2. And so if you have an axis, you keep the axis. The axis is ABC. But if you use minus ABC, then you need minus sine theta. That is to say, okay, so the rotation by theta around the axis, or the rotation of minus theta around the same axis, or of theta, the inverse, if you rotate by theta around the axis, the inverse should be rotation of minus theta about that same axis. The last one we're going to talk about later in this lecture, or beginning of next, is what's called the 4x4 rotation matrix in homogeneous coordinates. And it's simply a 4x4 matrix that has, the rotation matrix in the upper 3x3, upper left 3x3, and has all zeros in both the row and in the column that you add. And we'll see why that's going to be what we need also. But just keep that for later. But how many degrees of freedom of this guy? The same number as in R. How many were in R? 3. Every single one of these guys has 3 degrees of freedom. Of course, by now you understand a set of possible transformations always has a number of degrees of freedom, no matter how you represent it. The final piece of the story from last time is that we have these 3 representations, R and AV, the rotation matrix, the incremental rotation matrix, and the quaternion, and we have rules to go back and forth between R and A sub V, or A sub V and R, between R and the unit quaternion, or vice versa, or between AV and Q, right? So you need to locate in your notes where those rules are for doing those transformations, to go from one to the other. Okay? Any questions? Time I had it up. All right. So now we're going on with the quaternions. The space of all quaternions is the same as R4. It really is 4 dimensions because not only does it involve a rotation, which has 3 degrees of freedom, but it also encodes a scaling, a uniform scaling of the space by whatever factor you want, right? Expansion or contraction. That's one more degree of freedom. So 4 degrees of freedom. You can think of it as living in 4, and it has the properties of a vector space, meaning you can add quaternions element by element and get a quaternion. You can multiply quaternions by a scalar and get a quaternion. And when you take either you have inverse quaternions that are unique and a 0 quaternion that is also unique. That's what a vector space is. It's any set that satisfies those 4 rules. So it is a vector space. It has the standard vector norm of square root of the sum of squares. But it has particular multiplication and inverse operations that allows you to compose quaternions, to apply one quaternion, which is a scaling and a rotation, and then have another quaternion, and by the result, by simply multiplying the 2 quaternions. And to multiply 2 quaternions, erase all this now. going to need to have this operation, like we have here, be able to multiply two quaternions. And the rules for multiplying quaternions are just like the ones you're used to for all arithmetic, all algebra. That is to say, the distributivity applies. So we're going to get W2 times W1 plus W2 times A1I plus W2 times B1I plus W2 times C2. Whoop. What did I do here? This is J. Someone should have corrected me. Gee, guys. IJK. Right.
Then you get K on the first one.
Thank you. Okay, so there are four terms with W2 multiplying each of these guys. Then I get A2I times W1, A2I times A1I, which is A1, A2I squared, right? A2I times B1J, which gives you A2B1 times I times J. And C2K times, and B2J times, I was doing A2I times C2K, which is going to give me A1, A2, this is a 1. Right. This quaternion has 1s in its coefficients. This one has 2s. The point is that you're going to get 16 terms. And you're going to need to know what I squared is, what J squared is, what K squared is, what I times J is, what J times I is, and what I times K is, and what K times I is, and so on. And so, we will understand that I is 0, 1, 0, 0, right? 0 times 1 plus 1 times I plus 0 times J plus 0 times K. So we can write I that way and J that way and K that way, where the coefficients are the coefficients of 1, I, J, and K, respectively. And here are the rules. First of all, as promised, all of I squared and J squared and K squared are -1, just like imaginary constants. But I times J or I times K, okay, and so on, go by the following rules. There's this little circle that you remember that in order I, J, K. So I goes to J, J goes to K, K goes back to I, right? That's this little circle. And when you multiply I times J, it gives you the next thing around the circle. I times J is K. And J times K is I. And K times I is J. Right? See how it works? And the other part of it is, if you go in the opposite order, you need minus it. So I times K is minus K times I. I times J is minus J times I. If the arrow is in the wrong direction, when you want to multiply I times J, it still gives you something about K, but if it's in the opposite direction, this J times I, then it gives you minus K if you're going counterclockwise. If you're going clockwise, I guess. Yeah. Okay, so the result is that we can figure out what all 16 of those terms are. And just notice that there's a real term from W2, W1. There's a real term times A2I times A1I. It's A1, A2 times I squared, but that's just minus A1, A2. Right? There's a real term from B2J times B1J. B1, B2J squared is minus B1, B2. And there's a real term from C2K times C1K. C1, C2, K squared, that's minus C1, C2, right? There are four terms that together form the overall real term in the resulting quaternion. Yes? And then there's going to be terms in I. So W2 times A1I gives me W2A1I. A2I times W1 is going to give me W1A2I. Right? The other two are come from the J2 terms. You get B2J times A1I, and that's A1B2 times J times I, and J times I is minus, remember I said that wrong. B2J times C1K is B2C1 J times K, and J times K is I. Right? And then I get C2K times B1J, and that's B1C2K times J, but K times J is minus I. Right? So the order of the multiplication matters. I times J is not the same as J times I, but all four of those terms give you something times I. And when you collect those terms, you get a coefficient of I. The same thing goes for terms for J that are going to be formed by W2B1, B2W1, and then to get a J term, you need an I and a K, or a K and an I. Right, four terms there, and so on. Upshot is, you could write a program to figure out what the hell that is. Right? And it turns out that you can prove this result on the bottom if you have a W1 and the last three entries in the quaternion is V1. Right? It's an ordinary 3 vector. You get W1, W2 minus the inner product of the two vectors as the real term. And the other three terms come from W1, V2, W2, V1, and the cross product of V1 and V2. It'd be worth your proving for yourself that that's indeed the formula that follows from what all the algebra that I did for you just here. Okay, so I claim that a unit quaternion, one where W squared plus A squared plus B squared plus C squared is equal to 1, performs a rotation. How do I know? Let's all hear it for the duck rule. Right? Right? If it behaves according to all the specifications that we gave here, that it leaves sizes the same. So you put in something size t, and you apply the quaternion, you get the same size vector out. But what do you mean by apply it? And here I told you the answer. You apply a unitquaternion to the quaternion that's made by 0t, and multiply that on the right by Q inverse. And you show that it leaves sizes alone. If you apply it to two vectors, respectively to a t and another vector s, and then you look at the dot product between those two vectors results. When you apply to a vector, it's going to come out as a vector. It's going to come out as a quaternion with 0 in the first place, and the result, the rotated result in the other three places. Right? Yeah.
So is T a three-dimensional vector?
Say again?
Is T a three-dimensional vector?
Yes, T is an ordinary 3D vector.
And would 0 be our real term?
0 is the real term. So the Quaternion representation, the Quaternion representation of T1, T2, T3 is 0, T1, T2. Or it's written in the so 0 times 1 plus T1 plus I plus T2 times J plus T3 times K. Got it? Anyway, you show that it satisfies all of these rules. It leaves the 0 vector as the 0 vector. The rotation of two vectors and taking the dot product gives you the same as the angle between the original vectors, and the application to a vector of any size leaves the size alone. The size is T1 squared plus T2 squared plus T3 squared to the half, right? And so it's a rotation, because you can prove that it satisfies all those rules. Okay, so next one. The identity quaternion is 1, 0, 0, 0. Right? Because when you multiply 1, 0, 0, 0 times WABC, according to these rules, if this is one, let's see. I guess what we want is the identity quaternion is when you compose it, you get 1. And so if this guy is 1, 0, 0, 0, and this guy is any W1, you're going to get all the cross terms, but you're going to get 1 times W1, you get a 1 times A1, you're going to get 1 times B1 and a 1 times C1, and all the rest is 0. That is to say, it leaves the quaternion alone, because when you're multiplying the left, it leaves it alone. And if you play the same game on the right, and you let this guy be 1, 0, 0, 0, and this be W2, A2, B2, C2, you'll see that it also leaves it alone. So whether you multiply it on the right or the left, it leaves it alone, and therefore you have, it's the identity quaternion. Once you have an identity, an inverse is a thing which when gets multiplied by the original thing. When you have something in quaternion Q and you multiply by Q inverse, it's supposed to give you the identity. Right? You apply a particular quaternion, you take its inverse. For a Unitquaternion, it's just what I wrote here. It's you leave the real term alone and you change the other three terms. We'll come back to this slide in a minute, but this is the main thing to remember. A Unitquaternion has the real term being a cosine, and the other three terms have a vector v, which is multiplied by sine theta over 2. Right? And that vector is a unit vector. And it's the axis of rotation. V is the axis of rotation. That's a big deal. And it's on the slide if I push it up. Okay, so on this slide, you want to write your note. V is the axis of rotation, and theta is the angle of rotation. And the inverse to a rotation by theta around V is a rotation by minus theta around V. But cosine of minus theta over 2 is cosine of theta over 2, so the real term doesn't change. And sine of minus theta over 2 is minus sine of theta over 2. So the other three terms, the I, J, and K terms, all get negative, as promised here. W minus A minus B minus C. Or alternatively, you stick with theta, but you take the axis in the opposite direction. So now V turns into minus V. Say that right? I didn't say it right. Okay, so yes, I said it right. The inverse to a rotation by theta about this axis is the same as the inverse is the rotation about minus V, but again by theta. Okay, and this last thing is what I told you before, that when you want to rotate a vector v, you create a quaternion out of it. You multiply on the left by the unit quaternion and the right by the inverse. There's an interesting piece of mathematical history about this invention of quaternions. You know, we have these nice rules for one-tuples, scalars. And we know that multiplication by two scalars is commutative. The distributive rule applies, right? A plus B times C plus D. You can multiply all the pieces together and add them up, right? Then came up with duples. People invented complex numbers. There are two entries in a complex number. And you could talk about the multiplication, and you still get distributive rule. But you don't get, which one is get? Issue of associativity and commutativity, I think. And then someone said, well, there must be one with three. A plus BI plus ZJ. And this Scottish mathematician named Hamilton, also known for the Hamiltonian and various other things, spent years of his life trying to come up with something that still had the same kind of algebra with distributive and associative property, and couldn't find it. Oh, okay, let's try 4. The Quaternions. Sure enough, it worked. We have these distributive operators. He couldn't find one for 5, he couldn't find one for 6, he couldn't find one. Poor guy. Eventually, I don't know if it was Hamilton, somebody found one for 8. So there was one for 1, for 2, for 4, for 8 variables. And each time you lost one of the properties that you wanted, that you had before with scalars. Guess what next one you'd want to try is? Yep, it doesn't work. It's the end. 1, 2, 4, and 8, and that's all there is. It turns out that's been proved. Right? Poor Hamilton eventually committed suicide. He was not mentally stable, trying to find some of these other ones that we now know don't exist. I don't know if there's a moral for mathematicians here. Anyway, let's get back to this. Till now, I've been talking about Unitquaternions only. Their rotations. A non-Unitquaternion is one where you don't have this constraint of w squared plus x squared plus y squared plus z squared is 0. So a non-Unitquaternion is a Unitquaternion where you don't have, forget the subscripts, where you don't have this constraint. But if you divide by w squared plus a squared plus b squared plus c squared to the half, and multiply by w squared by a squared plus b squared plus c squared to the half. Okay, so I still have an arbitrary quaternion here, but this guy is a Unitquaternion, and this is a constant, a scalar multiplier. So a non-Unitquaternion is simply a Unitquaternion multiplied by a constant, and the constant is the square root of the sum of its 4 entries. All right? So this guy is Q hat, and this guy is called, this guy here is called the size. This guy here is called the size of Q, and this guy here is called Q hat, which is the original quaternion divided by its size, a Unitquaternion, and therefore its sum of squares elements is equal to 1, right? So the upshot is multiplying by a scalar gives you a quaternion. That's a rotation composed with a scalar multiplication by w squared plus a squared plus b squared plus c squared to the half. Okay, so now a quaternion is not just a rotation, it's a rotation composed with a scalar multiplication. Unitquaternions, the scalar multiplication is by 1. All other quaternions the unit multiplication, the multiplication is by w squared plus a squared plus b squared plus c squared to the half. And therefore, to take the inverse of q, you need an arbitrary q is going to be the inverse of q times q inverse is the thing that multiplies by 1. And you have to not only undo the scalar multiplication in both q and q inverse, if you will. You need to divide by size of q squared. Okay, so for a general quaternion, q inverse is this, and q is 1 over q squared mod q squared times w minus x minus y minus z. And for the particular case where you have a unit quaternion where the size of q, w squared plus a squared plus b squared plus c squared to the half is 1, you get 1 over 1, which is what we had before, w minus x minus y minus z. Got it? Okay, so we have quaternions. They are a representation q and minus q represent the same rotations. Figure that out yourself, right? Minus q rotates by the opposite axis and by the opposite theta. Yep, same rotation. So I'm going to stop these slides and go back to the slides on set 6. Because we got a few more things to say. And they're pretty important because they show us some of the real advantages of doing things in using quaternions rather than other representations. Okay, so I want you to hear this take-home message, and it is, if you have a choice of a representation, choose quaternions. Okay? There are 5 possible ones, and this is the one that is most beneficial. 1, because it explicitly represents things as axis and angle of rotation. And that's really nice, right? Because we understand that, right? And secondly, because some other things happen, and you'll see in a moment. Okay. So the first thing we want to talk about rotations is composition of 2 rotations. So we know that if we have an axis and we rotate by theta around that axis, and then we have the same axis and we rotate by theta 2 about that same axis, we get a rotation about that axis by theta 1 plus theta 2. This is what we talked about last time, right? And so we would expect that if you have 2 rotations where the axis is the same, you should have that simple multiplication of quaternions, which is simply an application of the composition, should work, and it does. So as long as you have the axis written in the original coordinates, so the Q2 and Q1 have the same coordinate system. The axis is the same in both coordinate systems. You can simply apply Q1 and then apply Q2 to a vector you get the result. But get a drop. Once you rotate by Q1, you have a new coordinate system. Your original coordinates, as we said, have become no longer horizontal, vertical, and depth. And representation in that new coordinate system of horizontal vertical is not the same as the horizontal vertical that you had before. And so if the vector, if you're going to apply where the the vector in the axis is in the new coordinate system, you got to play this game here. You got to rotate the axis back, then apply quick Q2, and then rotate it back forward. And if you multiply all that together, you get Q1 inverse times Q1 inverse its identity, and then Q1 times Q2. So depending on whether the second rotation axis is either in the original coordinates or in where the second one is in Q1 rotated coordinates, you get either Q2 Q1 or Q1 Q2 when you compose. A little tricky. Questions? Here's a fairly big deal. A quaternion is a point WABC it's on S3, a Unitquaternion is. Where it's either WABC is interpreted as a quaternion or as the vector WABC on this three sphere. And so, where do I have something to erase? I can't draw a four sphere, I'm sorry, beyond my abilities. Not on the board. But anyway, it's a point on the three sphere. And on the, if this is S3, not the two sphere. And now I have another rotation. It's also a point on the three sphere. And if I want to interpolate between those two rotations to get a successive, what I want is a shortest distance path between those 2 points. And the shortest distance path on a three sphere is just like a shortest distance path on a two sphere. It's a great circle, or a great sphere in this case. A great you want to get from here to Tokyo, right? you go via Alaska, not, even though we're at roughly the same latitude as Tokyo, you don't go straight west, right? It's just shorter to follow the Great Circle. And the same idea here, the best interpolation. And so the upshot is, you're interested in if this guy's a Quaternion and this guy's a Quaternion, and you want to interpolate between those two, you need to follow that Great Circle. And that's the formula where Q naught inverse Q1 to the T power, T goes from 0 to 1, is appropriately defined. And it turns out if that it's a linear interpolation on the coefficients of a sign. But the main point here is that Quaternions give you an easy rule for interpolation. You can see, for example, that at t equals 0, this is just q0 times something to the 0, which is q0. And when t equals 1, it's q0, q0 inverse, which is 1 times q1. So that's all fine. And we have to define what the half power or the third power or whatever is, and it comes out to be this. The next thing is, because Quaternions give you both rotation and scaling, if you want to apply a rotation and a scaling, you can do it with a Quaternion. That's good. But you can't do translation with a Quaternion. So you need to first rotate and then scale and then translate. If you're rotating about the center, the first thing you need to do is subtract the center to get the rotation. The Quaternion rotations are always about 0, about the origin. And so you need to take the center of rotation, move it to 0, apply the rotation. As far as the rotation is concerned. Okay? Done with Quaternions. Any questions about Quaternions? They're algebraically very nice. They're computationally nice. There exists, you take any reasonable mathematical system like mathematical program system like MATLAB or Mathematica, or anyway, you will find a set of functions in that for doing Quaternion multiplication by Quaternions by each other, computing inverses, multiplying a Quaternion times a vector, and so on. Right? I think I've given you everything you need to understand Quaternions between these two sets, the set 6 and the set, I think it's called 6b, but anyway, the Fletcher set. But now we're going to talk about this guy, which is used a heck of a lot in graphics and a heck of a lot in computer vision. And the reason for its popularity is partially because it allows you to do any of the other operations of rotation, translation, and uniform scaling. And it also allows arbitrary affine to be represented. And on top of that, it allows perspective transformations. Okay, so whereas quaternions are limited to, by themselves, only 2 of those operations, this one is more general. And it involves understanding vectors x, y, z as a 4-tuple x, y, z, w. Not the same w as we've been talking about quaternions. But an additional entity. And so now all vectors are going to be 4 tuples. And when you want to transform 4 tuples to 4 tuples, you're going to need a 4x4 matrix. Right? And so that's what we're going to have. So let me erase a lot here and get going. So your assignment 8 is going to involve applying quaternions. Okay, so what we're going to do is if we have a vector x, y, z, we're going to think of it as that. Or we're going to talk about those 2 vectors being the same. So the idea is division by a w gives you the same thing. And that's what we're going to need for perspective purposes. Okay, so we're going to have this funny situation where the vector xyz in original coordinates is either xyz1 or xwywzww, because when you divide through this one by 1, you get xyz, and you divide these 3 by w, you get xyz. Okay? And once you do that, if I want to translate by t, you can see that what's going to happen is you're going to get, for this I is the identity matrix. It's 1, 0, 0, 0, 1, 0, 0, 0, 1. You're going to get 1 times x plus tx there. And you're going to get 1 times y plus ty. 1 times tz, 1 times z plus tz, and you're going to get 1 here. Sure enough, that's x plus t. I mean, it's the representation of x plus t. If I throw away the 1. So translation is got by multiplying by this matrix. And if you put a w in all x, y, z, w, so if you have this, if you represent this by this, by this, by this, by this, then what you're going to get is wx, w, w. When you divide all of that through, it's still going to be x plus t. Okay, so whether I multiply by x, y, z with a 1 in the last slot or the representation of the same vector, I'm going to get the same result. Okay, so that's nice. I can do translation by multiplying by this matrix. The next thing is magnification, non-uniform magnification, with one magnification factor in the x direction, one in the possibly a different one in the y direction, and possibly a different one in the z direction. We've seen the importance of that for affine transformations. And there it is. Multiply the first coordinate by lambda sub x, the second one by lambda sub y, the third by lambda sub z. And when you multiply any vector by that, you'll get lambda sub xx plus lambda sub yy plus lambda z plus, and then 1. Right? Okay, so, and in particular, if we want uniform magnification, what do? Want to help me, Jennifer?
Me?
Yeah. What's your name?
Ann Hope.
Ann, I'm sorry, Ann Hope. My error.
I'm not
I'm-
sure.
Well, what do you want to, if you want to multiply by A, the whole business by A, what should lambda x be? A. It should expand the x direction by A. What should you expand the y direction by?
A.
What should you expand the z direction by?
A.
Okay, so you're going to have A1. Lambda x is the factor by which you stretch or compress, and it's all the same for uniform magnification. So it becomes A1 for uniform, and lambda x, lambda y, lambda z for non-uniform. Magnification. Rotation's easy. You leave the 1 alone and you rotate the XYZ component. You just stick the rotation matrix in there, in the 3 by 3. And you have 0 everywhere in the bottom row or in the right column except for 1 in the lower right-hand corner, which leaves the 1 alone. Okay, so it can do rotation using homogeneous coordinates. And the last major, so far I've showed you that we can do translation, rotation, and either uniform or non-uniform scaling, all in homogeneous coordinates. And since I remind you that ax plus b, which is affine, we can have R2. A is R2 times some lambda times R1 times x plus b. We can do the translation part. By that, we can multiply by the R1 transpose, which is just going to have R1 transpose 1, 0, 0. Then we have this lambda, which is lambda x lambda y lambda z 1. And then we multiply on the left by R2, which is going to be R2 and 0, 1, and 0 to 1. So we multiply by the sequence of first by this matrix, and then by that matrix, and then by that matrix, and then we add B1, B2, B3. So this has to be X. And then we add B1, B2, B3. At the end, which is to say, erase this all. Last thing in this lecture. What we're going to do is we're going to start with x, y, z, 1, and then we're going to multiply by our lambda, which is represented as lambda x, lambda y, lambda z, 1. And then we're going to multiply that by R2 with the 1 here and zeros here. And then we're going to multiply by B1 and remember exactly what the translation one was. There it is. Identity in this one. The identity 0 and B1. Right? So we start with x. We multiply it by R1t, which is this 4 by 4. We multiply that by lambda, which is this 4 by 4. We multiply by R2, which is this 4 by 4. And then we get the translation, which is this 4 by 4. And so we can get the whole business by 4 successive matrix multiplications for any affine transformation. And therefore, homogeneous coordinates allow you to apply any affine transformation. And we'll stop now. And we'll talk about perspective next time, and we'll see that perspective can be done with homogeneous coordinates as well. And so the take-home message will be, if what you want to do, everything, all of those, affine and perspective, in the same system, you use homogeneous coordinates. Until next time. Am I right, next Thursday's some kind of a,
A wellness day.
yeah, it's a wellness day, which means you don't have classes, right? So we have class next Tuesday, no class next Thursday.